Welcome to this explainer. Today, we're taking a step back to look at something so fundamental we rarely give it a second thought. We're going to explore gravity, and not just as a basic fact of daily life, but as the invisible architecture that actually builds and shapes our entire universe. Take a moment and just focus on your immediate physical reality. Right now, there's an unseen force pulling you firmly toward the center of the Earth. It's the reason you're staying in your seat right now. It's why the moon orbits our planet, and why the Earth orbits the sun. Without it, well, stars, galaxies, and black holes simply wouldn't exist. We call this force gravity, of course, but here is the fascinating contradiction we'll be exploring today. Scientists can predict gravity with incredible mathematical precision, yet its fundamental origin remains one of the absolute greatest mysteries in physics. Why does it actually exist at all? Part 1. The invisible force. So gravity, at its most basic level, is really just the tendency of objects with mass to attract one another. The rule here is remarkably simple. Anything that has mass exerts gravity. That includes you, the Earth beneath you, the sun, distant black holes, and, entire galaxies. The more massive something is, the stronger its gravitational pull. And as distance increases, well, that pull becomes weaker. This simple dynamic explains why apples fall from branches, but also why galaxies hold their shape across the vast void of space. For centuries, Isaac Newton's view really dominated our understanding. Newton described gravity as a pulling force, kind of like an invisible rope connecting objects across space. His equations were highly practical. They accurately explained falling objects, ocean tides, and the motion of the planets. But then, in 1915, Albert Einstein proposed something much deeper. He shifted our understanding from a mysterious pulling force to a fundamental bending of reality itself. Part 2. The space-time revolution. To really understand Einstein's vision, we first need to define space-time. Space-time is the combination of the three dimensions of space, so up and down, left and right, forward and backward. And it combines those with one dimension of time. Interwoven together, they form the literal stage on which every single event in the universe happens. To visualize how mass interacts with that stage, imagine placing a heavy bowling ball on a tightly stretched rubber sheet. The heavy ball creates a deep dip in the fabric. If you were to roll a smaller marble nearby, you'd see its path curve right toward the bowling ball. And this is exactly what happens in space. The massive sun bends the space-time around it. The Earth isn't being pulled by an invisible rope, it's simply moving through that curved space-time, following the natural, invisible path which eventually becomes its orbit. This profound shift in understanding is best summarized by a famous phrase from the physicist John Archibald Wheeler. He said, "Matter tells space-time how to curve, and space-time tells matter how to move." Part 3. How gravity shapes reality. Notice how the cosmic connects right back to the tangible. Like, why do astronauts float? They feel weightless not because there's no gravity in space, but because they're actually in a constant state of freefall around the Earth. On the flip side, the sensation of weight you feel right now is simply the Earth's solid surface preventing you from falling toward its center. And incredibly, gravity also affects time. The stronger the gravitational field, the slower time actually passes. This effect is tiny on Earth, sure, but it is a very real physical law. Furthermore, changes in gravity aren't instantaneous. The curvature of space-time adjusts at the exact speed of light. To put that into perspective, if the sun were to suddenly vanish, the Earth wouldn't instantly fly off into deep space. No, it would actually continue orbiting as if nothing happened for exactly 8 minutes. That's the time it takes for both light and the change in gravity to reach us here. Interestingly, it took exactly a century of technological advancement to prove this. Einstein proposed this curving of space-time back in 1915. He also predicted that highly violent cosmic events, like colliding black holes, should send literal ripples through the fabric of space-time. Well, exactly a century later, in 2015, scientists finally detected these gravitational waves for the very first time, confirming one of the most remarkable predictions in scientific history. Part 4. The quantum mystery. Now, despite its massive cosmic importance, gravity is bizarrely weak. Just think about a tiny refrigerator magnet lifting a paperclip. That tiny little magnet is easily overpowering the combined gravitational pull of the entire planet Earth beneath it. Gravity really only dominates on large cosmic scales because its effects accumulate. It always attracts, it acts over enormous distances, and unlike electromagnetism, it just can't be shielded. But its weakness points to an even deeper issue, which scientists call the quantum problem. The universe's other fundamental forces are neatly described by quantum mechanics, which is the physics of the incredibly small. Gravity, however, simply doesn't fit into that framework. Physicists are actively searching for a unified theory of quantum gravity that explains what space-time is actually made of. Leading ideas include string theory, which suggests particles are tiny vibrating loops, and loop quantum gravity, which suggests space-time itself is woven out of finite loops. But so far, the mystery remains completely unsolved.
Part 5. Why gravity matters.
Quite simply, without gravity, the universe as we know it would just be a void. Stars would never coalesce from clouds of gas, the sun wouldn't have the internal pressure to shine, planets couldn't form, the Earth wouldn't be able to hold on to its atmosphere, and life itself would be completely impossible. Plus, our modern world relies entirely on our understanding of it. The GPS navigation in your phone requires Einstein's theories to correct for the tiny time differences caused by Earth's gravity. If we didn't account for curved spacetime, our global navigation systems would fail within minutes. So gravity is tested, predictable, and essential. But we arrive back at our central paradox. Einstein perfectly explained how gravity works. He gave us the brilliant mechanics of curved spacetime, but he didn't explain why mass curves spacetime in the first place. The deeper reason for its existence completely eludes us. And so, gravity stands as both the best understood phenomenon in practical physics and the deepest unsolved mystery in science. Every time you drop an object or look up at the moon, you're literally witnessing the architecture of reality at work. Yet, the ultimate origin of this force remains totally unknown, which leaves us with one profound, unanswered question. Why does mass curve spacetime at all?